All right, so we are now in this lecture, in this video, going to have the last coordinate system for our force mass acceleration relationships, our first study of kinetics, first analysis technique of the kinetics involved, combined with the kinematics, to have a full dynamic description of a system or a particle motion is what we're limiting ourselves to here. Okay, so a bit of review here up on the page right now, which is of the kinematics in kinematics description, so describing the motion using polar and cylindrical coordinates. All right, so here's our velocity, and remember, just polar means we just don't have the third dimension. So cylindrical is just the polar coordinates adding on those last terms. And what we have is the plane here, the polar coordinates in the plane here, which is if the path of the particle is here at this particular instant, right, it has a particular position vector r, which we could break down into, it's the velocity here could be broken down into, so the whole description of motion is broken down to its components in the radial direction and in the angular direction. So, right, and so I guess I didn't add this on here, that the position is fully described as r itself, er. That's the one that's trivial here. Okay. So now let's write out our equations of motion to get at the dynamics involving the kinetics of the problem of the system here for this particle. Right, so it's always, no matter what we are, we use Newton's second law, summing the forces on that particle equals its mass times acceleration. Let's go in the r direction. We have sum of the forces, so here we're going to have three equation. Sum of the forces in the r direction is mass times acceleration in the r direction, which is mass times r double dot minus r omega squared. In the theta direction, this is sum of the forces in that theta direction, local to the point at that current snapshot in time, is mass times acceleration in the angular direction, angular acceleration, and 2r dot omega. And then finally in the z direction, this one is just a Cartesian direction, right? So summing the forces into and out of the page is the acceleration into and out of the page, which is mz double dot, right? So the coordinate is how far in and out of the page are. That's it, right? That's it for the theory. Now we just get to work through problems, through example problems. Really the hard part here is setting up the kinematics, which we have already are now masters at. Okay, maybe not. Maybe it's an ongoing process, but getting these relationships is difficult. And then the only added part is, hey, where do these forces act, and can we draw a good free body diagram? Okay, let's jump into the examples. All right, so example 1 here maybe is a little bit hard to visualize because I drew it, but some of the systems in the book, it would be very hard to visualize if I was one drawing it. But let's give this a go, okay? So we have a rod. It has a vertical section here, and then it's got an angled section off of the vertical, okay? That angle is a 3-4-5 triangle, right? So the slope is 3/4 of that angle, and then we allow it to, and it rotates about the central axis, right? So the thing would kind of would wrap a little bit pointing at you and then go around, right? So it's, I think of one of those like flying things, that little helicopters that you can make. But regardless, there's a little collar on the rod here, on the angled rod portion, weighs 2 kilograms. What we want to do is determine the rate of rotation, the angular velocity, so that the collar kind of hangs out where it is, doesn't slip down. So if you rotate the thing too fast, the collar actually head on out, right? As its inertia from rotating so fast overcomes any friction and the weight of itself, right? But if it's too slow, the collar would just like slip down, overcoming any friction together with its, and then the weight would kind of be working towards it, right? So if you just set it on there when the thing wasn't rotating at all, the collar would just slip down, assuming that the friction wasn't too great. So we're given the friction coefficient. This is a static friction coefficient. Mu is 0.2. well, we say static coefficient, right? This is take the normal force and excuse me, the normal force, multiply it by 0.2, and that gives you the friction. So this is a, you know, a material specific quantity. Okay, regardless, yeah, that's the setup here. So let's start this analysis, right? Well, we're gonna have to get to a free body diagram for the collar. Hopefully that should be apparent. But let's first start by just maybe a kinematics, and so doing that we'll be applying these equations. But let's start with just a kinematics description that'll help us. So we'll look at the kinematics from above in a way, or maybe just the geometry from above. So a top-down view here. Problem description is above us. Okay, so this is our central point about which we're rotating, or the collar is rotating. So what we're just going to do is just draw the collar's path. Let's go 2 boxes out. This is just that collar's path about the central axis of rotation. Okay, this is some radius that's constant r, and we'll calculate r in here in a second. It's 0.25 meters, so 25 centimeters up the rod on a diagonal, but we need to, you know, from a top-down view, we're going to need to know what r is. Our coordinates, right? We're going to be doing our analysis in the polar coordinates. Let's do actually cylindrical coordinates. So there would be our position vector in this plane. So there's our radial coordinate. Our angular coordinate is normal to our radial coordinate. And why is that? Well, because there is theta. Okay. And so increasing theta, so maybe draw a tiny little arrow. Increasing theta would be in that normal direction. And then additionally here, right at here, we also put the k hat direction. Now, this is, I think, the first time I've drawn it. This little notation means it comes out of the page. I might have drawn it before. Out of page. Okay, so we're going to see that quite a bit when we have three-dimensional. Okay? All right, anything else? Oh yeah, we want to determine what r is. So let's take this triangle here, that we have here, and recognize that we have a similar triangle hidden right here. This 0.25, and then r is the horizontal projection. These are similar triangles. Similar triangles. Okay? So that means that we can do a proportion, right? That r over 0.25 is 4 over 5. Or r is 0.2, 4/5 of a quarter, which is a fifth. Okay, great. So that's the geometry. We're being really careful, you know, with these three-dimensional. I mean, there's really a three-dimensional structure going on here. It's good to draw as many pictures as possible. The next picture that we always need in our kinetics problems or dynamics problems is a free body diagram. What we're going to do now here is take a different approach. I'm going to take the approach of looking along the E theta direction, and I'm doing that because there are no forces here in the theta direction, right? So what I mean is we're going to kind of become an observer right behind it looking down E theta. So we're going to come and view it right there, and I'll draw the coordinates in there as we get there. Okay, so this is our collar isolated as a point. And let's just do it right away, right? So this then, k would be up if we're looking straight towards the theta direction, the angular direction. And then this is the radial direction heading out. Okay? Now the forces, we always have gravity acting always downward. And then the friction is going to be along the surface. So, and assuming we're rotating, right, and preventing motion from going downward, we're trying to prevent motion going downward, the friction is going to be opposing that. So this is the force due to friction. We'll just put a capital F there. And this is that 3, 4, 5 triangle. Okay, then normal to the surface, so then this is the rod here. This direction is the rod, so normal to that is our normal force. Okay, capital N. And now this triangle has been flipped, right? Because it's normal. So now it's a 3, 4, 5 triangle. Okay? And that's just because these are normal to one another, perpendicular to one another. Okay, great. I think that's our free body diagram. That's everything, right? Nothing else acts on the collar. We can now move into our equations of motion. Okay. And really everything we need is here. So let's do equations of motion in the z direction, right, which is the k hat direction on our free body diagram. Right, that looks like this. If we sum the forces in the z direction, or the k hat direction, right, now the normal force projection is going to be 4/5 of the whole thing, right? You could, another similar triangle, let's just do this one time, right? So we have, this is just an example, if this is n, right, then this is going to be the n in the z direction, which is a similar triangle to 3, 4, 5. So that means nz is going to be 4/5 of n. Okay, it's nice that we don't have to actually do any trig here. Okay, our friction then, and this is in the positive k direction, friction is also in the positive direction, but it has a component that is 3/5 of its total, for the same reason that n was 4/5. And then we have to subtract off mg. Okay, those are all our forces, so kinetics part done for the z direction. This equals mass times acceleration in the z direction, which we know is equal to 0. It doesn't accelerate, it doesn't leave, it doesn't go off any in the z direction. If there's any acceleration, it's just around the circle in the plane. So we're imposing that there's 0 acceleration in the z direction. So this is at the impending slip limit that we're doing an analysis at, right? We want to know what is the rate, the rotation rate at which slip is just about to occur as we lower our velocity, right? Lower our angular velocity. Okay, this friction here is going to be our static friction coefficient times the normal force. And so from that we can solve this relationship, this left-hand side here equal to 0. N is going to have a 4/5 multiplier plus a 3/5 times mu s multiplier, and that must equal mg. Therefore, our normal force is, yeah, let's be specific here, right? Let's just write this all the way out. This is going to be 2 kilograms is our mass. G in our SI units is 9.81 meter per second squared. Divide by this, well, 4/5 is 0.8. 3/5 is 0.6, and our mu s is given in the problem statement as 0.2. We have kilogram meter per second squared. That's a Newton. Great. That's the unit of a force, of a normal force. And so everything checks out. 21.3261 newtons. That is going to be helpful as we move into the other direction, right? So we can use the vertical, the z direction, to give us the normal force. Okay, I ran out of space. Got to finish the problem here on this next page. Okay, let's go to the theta direction, just for completeness. Could have done this last, but let's just say we weren't, you get comfortable with this and you realize, hey, this isn't going to give us too much. But what does it say, right? There's no forces in the theta direction, in the angular direction, right? So that must equal mass times acceleration in the angular direction, and that must equal 0. Okay, well, this is great because this tells us that we must be rotating at a constant omega, which which is given in constant angular velocity omega. So we're just doing really a check here. This allows us to check the assumptions made, or that we didn't miss a force, let's say, right? Because if that's what the problem statement says and you get something that's not 0, we've got problems. So sigma a of theta is 0. Check. All right. So really, our problem comes down to the radial coordinate. Sum the forces along r. We have minus n 3/5, right? Pull back our diagram. So it's like the horizontal of this one, right? Here it's pointing backward to ER, unit vector in the positive r direction, and it's 3/5 of the total one, so that's down here. This is NR, right, which is now similar to this triangle, so it's 3/5 of n. So NR over n equals 3/5, so you can solve for NR is 3/5 of n, yeah? All right, working through similar triangles. Isn't that nice? Being able to avoid the trig. I like that. Okay, minus n 3/5, and then we have our friction force 4/5 of the total magnitude there. That equals mass times acceleration in the radial, which we know to take on m r double dot minus r omega squared. Look at that. Looks like the r. Looks like a frowny face. Okay. Right? Oh, not happy doing dynamics. Okay. So this then allows us to solve for omega here because everything else is known, or at least we can write this in terms of the normal force. So if we solve here for omega, which is what we are, the goal of the whole problem is, right? Let's see. First of all, we're going to have minus n 3/5. Oh, actually, there's a negative there, so that'll become positive. So that'll be n 3/5 plus another n here, that's times mu. Oh, and it's not plus, that switches to a minus. Minus 0. Okay, let me start over. I know I got plenty of space on this page because we're almost done here. Let's write it like this. Omega is going to be equal to, let's convert the 3/5 to a 0.6. 0.6 times n plus 0.8 mu s times n. And that's not a plus. I made the mistake again. That's a minus. We will have a term where we subtract over mr double dot, but then we make it positive. So there we flip the sign when we multiply through by that negative. Okay, so that brings everything over to this side, and then we divide by m and r. And then we'd have to take the square root. Okay, so all the algebra done in one step. Please check the work. But r double dot, right, that is 0 because r is constant at this limit of impending slip. So r constant, that one just drops to 0. And we have units, we have numbers for all the rest. So omega is going to be 0.6 minus 0.8 times 0.2. All of that multiplies our normal force, 21.3261 newtons. Divide by 2 kilograms, and our radius is 0.2 meters. And we might as well just call this big R there, right? That is the radius of the motion, right, which we determined, where was it? Right here. Okay. And quick check of the units. We'll do that in a second. The number turns out to be 4.85. What are the units? No units on terms of all these. These are those ratios coming from the similar triangles and our static friction coefficient, which is unitless as well. We have a Newton kilogram per meter. So a Newton is a kilogram meter per second squared divided by a kilogram divided by a meter. Kilograms cancel, meters cancel. We have a 1 over second squared. When we take the square root, we just have a 1 over second, or radian per second. All right, and that's it. All right, so in the second example now, got a fun little system here, right? I wish I actually had like a demo here, but we have like a shaft, right? So like a rod of some kind. With on top of it, there is a rope attached, and we're swinging. You can think about your hand holding on, right, to this rod and swinging it, right, and so giving it some sort of rotational motion, right? Or maybe it's just a rod being rotated, being driven by something, right? And that we got this geometry, right, where the actual angle of rotation here is at 85 degrees, so not exactly horizontal, and that's because the mass weighs something, right, and the weight is pulling it down. Has a length of the rope of 0.4 meters, and yeah, what else do we want to say? Causing, and this is supposed to represent the circle, right? So the mass is kind of shooting around, okay? What we want to determine is what force is being carried in the rope and what the speed of the pendulum is, okay? So we always start with helping ourselves out by drawing some nice pictures here. Let's take a top-down view first. Okay, this is going to be a top-down view, so all we're going to see here, let's try to keep the colors consistent here. This would then be a circular path. What we're drawing here is the mass itself, and the path that it takes. And this is the radius, as I've drawn it, of motion. Now let's go back to the original diagram and put on here our coordinates. Okay, and if I've done this drawing well, right, the radial direction heads straight out. This is E hat R, that's the radial direction. The theta direction goes kind of a bit into the board here, right? E theta, right, if I were to draw that. And then straight up, right, because gravity here is acting straight down. I barely made it on the screen. G, pointing straight down. And then K is the direction of, against which gravity acts. Okay, so we are definitely in cylindrical coordinates here. So on this projection, right, we're looking down K hat. All right, and then at some place in the motion, right, here is the radial direction, and there is the angular direction, theta. Okay, so now what do the reason might just be to give us more perspective to draw this out, but we also are going to need to this highlights that the radius of the circular path isn't 0.4 meters, right? But it's going to be the length of this triangle here, the leg of this triangle, right? Where that triangle looks like that, there's the 85 degrees. We know this to be 0.4, and that's the R we're looking for, right? So since this is the opposite side of the angle, right, sine of 85 degrees is R over 0.4. So we can solve for R as 0.4 times sine of 85 degrees, which is close, but not all the way, right? In fact, if you did the calculation at 0.4 meters for R, you're not going to be too far off. But this is technically what we need to analyze it with. Okay, this is not a free body diagram. We still need to do that, right? So let's do the free body diagram next. Okay, this is now going to be the mass. Now we are looking, let's look along E theta. And the reason we're doing that is because there's going to be no forces in that direction. So there'll be no forces coming at us or going away from us. So it's a convenient choice here. Okay, and so basically we're like looking here, right? What's pulling, what's acting on this plane here are all the forces, which is the weight and the tension. Now the tension in the rope is almost horizontal here, but our coordinate directions, right, this is the K hat direction, this is the radial direction, and so there is that angle of 85 degrees. Okay, now let's start the analysis now, running first to our equations of motion. Okay, let's start with the K hat direction, right, which is summing the forces, well, it's the Z direction really, in the z direction is going to be minus mg, and then we have the cosine projection, or the cosine component of our t, right? And that's because, in the z direction. Do we need to draw that out? Let's see. Let's draw. Is that 85 degrees? Oh, I did it. Oh, of course. That's wrong. That's what didn't make sense. 85 isn't there. Look how small that angle is, right? 85 needs to be the big angle. Intuition should have been screaming. In fact, I'm sure for many of you it was. And that's the, we'll be creative there. That's that angle, 85 degrees. I got it right in my notes. I'm just lose myself here sometimes, right? So 85 degrees is the big angle. And so since I made the mistake, let's be really careful. T is sitting here. The component in the vertical is right there. This is like t sub y. If that's 85 degrees, this is t sub x. T sub y is 85. That's the adjacent, not 85. Ty is t cosine 85 degrees. Okay. Ty is t cosine 85 degrees. Great. All right, and that's where it shows up over here. And it's in the positive direction, right? In the positive y coordinate direction, right? Okay, so those are our forces. That's the kinetics of the problem. That must then sum to our mass times our acceleration in the z direction, right? Which is 0. We're not moving up and down as we're rotating, right? The y-axis is always staying, the y-coordinate, it's not y, it's the z-coordinate is always constant, our elevation. All right, so we're imposing here that that is 0 due to the description, that's how the motion is, right? Our observation of the motion. This then allows us to solve for the tension in the rope, which is the force carried in the rope, mg over cosine of 85 degrees. Which, let's plug it all in. 1.2 kilograms is our mass. 9.81 meter per second squared is the acceleration due to gravity. Cosine 85 is going to be close to 1. Is going to be close to 0. And so that's going to make this a big number because we're dividing by something that's small. 135.07 newtons. Okay. Now, part B, we're going to need to sum in the other direction, right? So let's now sum do our Newton's second law in the radial direction, which is the only other direction we have available to us. In the theta direction, it's trivial, right? Summing here, all we have is minus t sine of 85 degrees, right? And that's this one. This is going to be t sine of 85 degrees because we are now opposite our angle of 85 degrees there. And this is going to equal mass times acceleration, but we are in acceleration in the r direction, which is mass times r double dot minus r omega squared. All right. Well, for this motion, right, for this motion as we fly along here, our radius is always this capital R. R equals big R, which is a constant. Little r we think of as the variable, as kind of a coordinate direction in polar coordinates. We have, for circular motion, that coordinate is just constant. Okay, so what this allows us to do is solve for omega, which is what, well, it's not the speed of the pendulum, it is the angular velocity of the pendulum. So omega is going to be the square root of t divided by mr. Oh, let's cancel this out so it's really clear. This allows us to say that's 0, all right, because it's constant. With all of that, we can then solve for omega. What's that going to be? That's going to be, the negatives are going to cancel. We'll have t sine 85 divided by m capital R and square root the whole thing. T divided by m r sine of 85 degrees. right? T value is here, 135.07 newtons. Our mass is 1.2 kilograms. Our radius is 0.3985. Plug all that in. We've got an omega of 16.77 radians per second. That is our angular velocity. That is not our speed. That is not the speed at which the mass is moving. Speed is a meter per second. It's a translational or a linear velocity, instantaneous tangential velocity to the motion, right? So to get there, we need to take v. The relationship between omega and v when we're in circular motion, v equals r omega. And when we're at a constant radius, that's r, capital R omega, right? There's your coordinate. This is the constant value of that coordinate for this motion. And, right, so we're just going to take this value, multiply it by 0.3985, and we find a value of v equals 6.685 meter per second. Great. All right. Again, complicated looking system. Break it down. Key components is the free body diagram, drawing as many pictures as possible, doing the triangles, right? Using intuition, right? Where was the picture that I drew incorrectly? Was it this one? Oh, it's this one right here, right? It didn't make any sense that 85 was here. That's a tiny angle. So if we're drawing them, reasonably accurate, this isn't 5 degrees. That's not actually 85 degrees. 5 degrees would be much smaller. But I made it small enough where the intuition would jump out at me, like I think I labeled something wrong or drew something wrong. So that's always helpful. All right. So that wraps up this problem. Okay, in this last example for the force mass acceleration dynamics relationship, so first shot here at kinetics combined with kinematics, specific to polar coordinate systems, is I'd like to go about calculating orbital speeds of objects in circular orbit around the Earth. So at the end of this, we'll pull up a nice visual here of all of the, well, many different things in orbit around the Earth, but one of them is the moon, one of them, and then a whole bunch of satellites, GPS satellites, and it's pretty amazing to think about hundreds, thousands, maybe even of objects out there that all orbiting, but they all follow a pretty similar pattern. What's great about once you get out into space like this, even just outside of the Earth's atmosphere, is actually the forces become pretty trivial, and like these idealizations we make where there's no friction, no drag, they become pretty accurate because there's no air to get in the way, and the physics come down to gravity and inertia and any thrust that's provided here. So yeah, let's dig into this. So radius of the Earth looked up to be 6,378 kilometers. The mass of the Earth is huge, 5.9 times 10 to the 24th kilograms. We'll need to use that. We have and then we've just represented this as now the thing, whatever it is, whatever object it is orbiting at a height h. So for a particular example, the International Space Station orbits at 340 kilometers. So you can see it's actually pretty small compared to the radius of the Earth. Right, so it would be hugging it pretty close. Whereas the moon, I need to look it up, is 384,000 kilometers. So, 3 orders of magnitude further away, and much further away than the radius of the Earth. So the moon would be, way out here, and then the Earth would be just like a point on the page, whereas the International Space Station would actually be like really close, probably like right in there. Like it's less than 10% of the radius is the orbital, orbit altitude or whatever of the International Space Station. Okay, so I have highlighted here the height from the surface. Now be careful, we're putting the height above the Earth's surface, so when we're this close, that actually the orbital radius about the center, the center of the coordinate system here, this fixed point at the center of the Earth, that's actually mostly taken up by the radius of the Earth. So when we talk about its radius is going to be, now we can put this on here. The radius here is actually our Earth plus the height. Yeah. Okay. We've done this for a particular location here. Okay, which is some satellite, and it has in polar coordinates ER and E theta. Those are your radial and angular coordinates, or unit vectors. Okay, so when we go to our free body diagram, kind of already have it there, right? This is what I mean, like the actual force, the kinetics involved are not that complicated, right? When we get into just things just orbiting nice and simply here. If this is our radial direction and this is our angular direction, then the force, the only force involved, is the one that heads straight against the radial direction, and that is gravity back towards the center of the Earth. This is the force due to gravity. Now I didn't put mg here because we are in a period where we're in a regime here where it's not fair to just put mg, right? We have to go to the universal law of gravitation. So our equations of motion, we have well, trivial in the theta direction here. There's no force, so we're just going to focus on the radial direction, which just says our sum of the forces in the radial direction is minus Fg, and we will dig into this in a second, but this must equal mass times the thing orbiting, or the satellite. So the mass of the satellite times r double dot minus r omega squared. Okay, this r, so r is re plus h, which is a constant for orbits, pure orbits that aren't changing. So this is then 0. Okay, and so we can write this as the mass of the satellite times its tangential velocity, or its speed, I should just say, which is its tangential velocity, is speed squared over r. Okay, and this is constant. And it's negative. Gotta sneak a negative in there. Right there. Okay. Now let's dig into the kinetics, right? What is this force? Okay. Fg is, from the law of gravitation, is going to be the gravitational constant times the product of the two masses involved. So we have the mass of the Earth divided by the mass of the satellite. By the way, the moon is also a satellite. It orbits, and therefore it belongs in this equation as well, right? Now, I should also say, like we say, oh, this is so simple. It's also not very simple, right? It depends on what level of detail you need, because as like the satellites go around, they are also being tugged on by big massive objects like the sun and a different gravitational force. They're also being tugged on maybe by like the presence of Jupiter. They're being the moon has all of these effects of the rotation slowing down because Earth has an ocean on it, right? So because there's the tidal influences from the moon and the sun being there, slows the Earth's rotation down, slows the kind of the energy, it redistributes the energy in the moon-Earth system. And so like when I said like the dynamics are so simple, it depends on like what type of question you're trying to ask. And if we're talking just like, the time period of a satellite for, being up there to be a GPS satellite for a little bit of time, those other types of forces, do we need to consider them or do we not? And so this is just the first go at it, right? So this is our Newtonian gravitation in the most general sense. Okay, and this G is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared, and it is the universal gravitational constant. Okay. Okay, so let's combine all this now, right? So we have our only, and now we have the two negatives cancel, so that's good. So we have G, mass of Earth, mass of the satellite, over the total distance to the center of the Earth squared equals mass of the satellite, speed squared over r, which is re plus h. Okay, now we have two of these r terms on the bottom, one on over here, so one of those cancels. So I canceled the power of 2 with that. Now we have a mass of the satellite on both sides, so that cancels, right? So the speed has no dependence on the mass of the satellite itself. So I don't care whether it's the moon or a tiny like little box satellite that they're throwing up, a whole bunch of them now. Solve for v by taking the square root of the other side. G, mass of Earth, over the radius of the Earth plus its height. And that's it. I mean, we could be done. Well, let's spend a little bit of time talking about what this value is for specific ones, for specific satellites at different elevations. So let's pick I don't know, think of it as like a table, making h values and then what their associated speeds are. So if they're in orbit at 200 kilometers, plug 200 into h and plug everything else in, the speed is 7.8 kilometers per second. That thing is zipping around, which is 17,400 miles per hour. Okay, and again, we're going to follow this up with a look at what types of satellites are at these different elevations. I just want to get them all down. If you plug in 340, remember that was the International Space Station. This is 7.7 kilometers per second, which is 17,224 miles per hour. So this is the ISS. Let's do an H of 20,350 kilometers. Taking it way a big step up. Velocity here is 3.9 kilometers per second, which is, right, these are just all really fast compared to the scale that we live on here on Earth in our daily lives. The reason we went to this one, this is where GPS satellites go, right? Which I think is amazing, right? We know our position just with the phones or whatever else, GPSs are used ubiquitously nowadays. It's pretty amazing, right? The difference between how far up those are compared to the International Space Station. I mean, it's a world apart, right? What's cool about these is that they put them at such a place to orbit twice per day. Exactly. Well, about twice per day. So about every 12 hours. Right, and it's governed by how far up. So what's cool about like the orbital mechanics like this is actually you give the satellite enough energy and it'll find its orbital altitude, right? What that h value is. It'll find the right one. It'll lock into it, right? So if you don't give it enough kinetic energy, you don't give it enough kick with the velocity here, it won't reach the h you want, right? If you give it too much, it'll go to a higher h. These things are locked together. Right? Give it this much velocity, and well, assume it has that much velocity once it leaves the Earth's atmosphere, it'll go to that particular height. Those things are one and the same, independent of the mass, right? It's just governed by the gravity constant, that's universal. Mass of the Earth, that's the same for any satellite about Earth. Radius of the Earth is about the same, so it's just h and v. It's just two things. It's so simple. I think it's so lovely of a result. Let's do another one, which let's analyze the geosynchronous orbit. Okay? Geosynchronous or geostationary orbit. Now, geosynchronous means we're fixing the longitude lines, which means it's rotating with, like, let's do this. So the satellite would always be, we can do this. All right, so the satellite might, something like that. Right? It looks like a bow tie. But you allow it to then move, oops, wrong color. Move here so it, can rotate the Earth that way, right? That way. But as the Earth spins this way along its axis, it stays with it, right? So it stays above some longitude, but you allow it to move that way. And there's some advantages to that, right? A lot of the satellites used to take images of the Earth, you keep them going around the Earth in a geosynchronous orbit, but you allow them to sweep along these lines of lines of longitude to maybe take certain types of pictures or do certain types of analysis. Whereas geostationary is completely stationary. So this is just a fixed position. All right, so that would be just one of these positions always stays there. So it rotates and it does. So what happens is geosynchronous, you don't have to have as much control, right? So once you get it up into, get it to a geosynchronous orbit is a particular velocity it has, right? It goes to a particular height and it'll just spin with the Earth, and that's what we're going to determine here. And then to make it geostationary, you need to give it extra energy to stay right there all the time, right? You need to be much more careful with it. Geosynchronous, you just don't need to be as careful. Okay, so let's see. How do we do this? Well, the velocity that you need to give it is going to be, well, this is always r omega, which is going to be the radius of the Earth plus that h that we're looking for, and then we want to set omega to be 2 pi rads per day, right? So that as the Earth rotates in one rotation per day, so does our satellite rotates in one rotation per day. What's one rotation per day? 2 pi radians, right? It makes one sweep, right? And this isn't perfectly one rotation or 2 pi radians per day. There is a little bit, of wiggle room there due to it not being perfectly. Well, I guess it is. I mean, I guess it is perfect because of the way we define day. I guess I haven't put in here the hours yet. It gets a little bit tricky when we actually multiply this out, right? So when we say a day, how long is that? I'm going to say a day is 3,600. That's 60 seconds per minute, 60 minutes per hour. That gives you 3,600, and then 24 hours. So 3,600 times 24 is the number of seconds in a day. And then, by the way, this whole thing is squared. Oh no, not yet, right? That's just it, right? Okay, and that's it. When we put it into the equation, we'll have to square it. Okay? So what we're doing here is imposing this relationship. So when we have our, velocity is gme over re plus h square root, well, now we just say, well, that the velocity has to be this in order to get to the height of a geosynchronous orbit, right? So we have, let's see here, radius of the Earth plus the unknown h that we're trying to solve for. What is the altitude for geosynchronous orbit? Squared 2 pi over this 3,600 times 24. This is radians per second squared. And that must equal gme over re plus h. Becomes a cubic, right? So it becomes cubic, so we could solve for this. Radius of Earth plus h cubic equals gravitational constant times the mass of the Earth all over 2 pi 60 times 60 times 24 rad per second quantity squared. And solve this. Actually, it's not too hard to solve. This is all calculatable. Take the cubic root, subtract off the radius of the Earth. We find h to be, from this calculation, 35,854 kilometers. And that is the height for our geosynchronous orbit. Cool. Okay, so we'll confirm this when we go to the. I wanted to mention one more, right? Height of the moon is 384,000 kilometers. So from this relationship, you can also determine that the speed of the moon with respect to the Earth is just about 1 kilometer per second, which, seems like a lot. 1 kilometer per second. We've never gone that fast with respect to the Earth, or I haven't. But compared to these speeds, this is actually quite slow, right? Okay. All right, so I thought it'd be fun, a good idea here to end this problem with just a look at the different orbits. So down here on the bottom here gives you a scale. Like everything here is to scale, by the way. I think this picture just pulled off the internet, off Wikipedia. I think NASA made it. Give you an idea. I'm not sure who made it actually. Give you an idea of the different heights of orbit, so the different altitudes of orbit for the different satellites, where the moon being the biggest satellite we have and the furthest away probably. But this is to scale. So right, so here's the moon, here's the Earth, and then we call low Earth orbit there. And you can see here, that's the blue. Medium Earth orbit is this big chunk, and then we just have the lower end of the high Earth orbit. All right, so that gives you a perspective. Now, we determined that the moon must fly around at this height of 3,804,000 kilometers. 384,000 kilometers. It flies around at 1 kilometer per second. And then as we get closer in, the orbital speeds go faster and faster, right? So to keep it in a low Earth orbit like here, which is where like the International Space Station is, the Hubble Space Telescope lives right in here. You actually have to give it quite a kick, quite a velocity to keep it close, but stay also in orbit. All right, the slower the speed. The further out it is, the slower the speed is to stay in orbit, right? So like our GPS satellites are out here. Well, we have a lot of them, and then they're out here. They're on a semi-synchronous orbit, meaning that they orbit the Earth in exactly 12 hours, so twice per day. And then the geosynchronous orbit is out here. We determined our geosynchronous orbit to be 35,854 kilometers. I think they were just a bit more careful with that conversion of rotations per day, right? And it makes up that like little bit of a difference. But yeah, I think everything matches here. And then I think the main concept here that's important is like the closer you come in, the bigger velocity kick you have to give it, which maybe takes a little bit more energy. Another way to require a lot of energy is to make it the satellite more massive. So when we're talking about the moon, there's a lot of energy in there because it's more massive than any of these satellites. And then one other thing was you can go to where is Roadster. I forget what this website is, but you just search up where is the Roadster. Elon Musk, founder of Tesla and a bunch of other crazy things, SpaceX. He sent up as a publicity stunt one of his Tesla Roadsters in an orbit around the Earth to kind of prove that, the SpaceX rocket technology was working. And they actually made a bit of a mistake. I think the actual orbit was a bit bigger than what they thought it was. But yeah, so here we kind of think like the orbits now are of the planets around the sun. So the sun would be, it would take the place of the Earth in our calculations, and you'd put the planets in here. And they actually put the Earth, the Roadster, in this elliptical orbit that gets kind of skewed by. So it's definitely like rotating mostly around the sun, revolving around the sun, but it's so it's an orbit around the sun, but gets affected by all these planets, and then the original kick that they gave it. But yeah, this is kind of funny. There's actual, true car, a Tesla car out there in space flying around, and they were hoping to have it make some close approaches to Earth and keep it a publicity stunt going forward. A kind of a combination between Tesla and SpaceX, two of companies owned by Elon Musk there. But bit of a publicity stunt, but a fun one. All right, so that kind of wraps up our discussion of force mass acceleration relationships in terms of the kinetics involved combined with the kinematics that give us our descriptions here of dynamics. And then this kind of wrapped up our look at that in terms of polar coordinates, but it also wraps up our full discussion of the force mass acceleration. Next will be work and energy, which actually relates nicely to the energies I was talking about, potential energies combined with kinetic energies related to these orbits.